So good morning, everyone. Welcome back to Math 115. Just 2 days of class this week, and then we'll be on Thanksgiving break. So I don't know about you all, but I'm excited to go see my family. Sort of. No, I'm kidding. It's going to be fun. I have for some reason, this is going to be our biggest Thanksgiving in quite some time. So I don't know whether to be excited or a little bit scared for that. But anyways, it'll be interesting. We'll see how it goes. Hopefully you all will be able to get some rest and some relaxation in order to be ready to finish out the rest of the semester when we come back. So today's class, we're going to talk over some more trigonometric identities. I've been really swamped with a lot of other things, so I have not been good about putting up the homework and giving it proper due dates. I'm going to do that today. 5.1 is already on there, but I might remove a couple questions, and then I'll take a look at 5.2 and put that together, and it'll all be due on Tuesday after the break. So then I'll do a homework assignment for 5.3, which will be due on Thursday of the week following Thanksgiving. So your next assessment is going to be a group quiz, quiz 7 on November 29th. So the sections for that will be something like, did the exam go up to what, the exam went up to 4.6, so it'll be 5.1 through 5.3. No, it's going to have to be 5.1 and 2. Okay, so that'll be what the quiz is on November 29th. Group quiz, you can work with up to 4 people in a group. My office hours are, I'm not going to have office hours on Tuesday this week. If you want to have office hours with me this week, I need you to send me an email, because it needs to happen today. Or it needs to happen remotely, or something. We'll figure something out if you need to have office hours with me this week. So just send me an email for this week. If you can't come to my office hours or we can't work something out, then tutoring center is your best bet. Regarding class on Tuesday, i.e. tomorrow, it's going to be in person. So we had said that maybe we would do asynchronous if everyone agreed, but at least one person wants to have in-person class tomorrow, so that is what we are going to do. If you don't want to be here, well, you can read the attendance policy of the class and make an informed decision for yourself. I will still record the lesson as usual and post it to my YouTube channel. Regarding the exam, I graded the exam, and actually it was better than I expected. It was pretty good. The average was 73%, which for a college level math class is pretty high actually. So I was happy with that. I'm not going to pass the exams back right now. I'm going to pass them in class tomorrow if you're here, or if you're not here, then on Monday following the break. That is because I still have 1 or 2 students that need to take the exam that are going to take it either today or tomorrow. Or not today or tomorrow, just today. And yeah, so that's when I'm going to give back the exams, is in class tomorrow. Was everyone able to see their grade on the exam on Blackboard? Okay, good. All right, any administrative questions before we start in on content for today? Yeah. When is our final exam? Our final exam, let's check. The 6th sounds right, but let's be sure by checking the syllabus. And hopefully they didn't change it on us. Tuesday, December 6th, 9 a.m. in our Tuesday classroom. So that's the 2nd floor of this building. Note that it's a different time than our usual class start. Usually our class starts at 8:30. The exam on Tuesday, December 6th starts at 9 a.m.
Will you
It's going to be longer than that. It'll be 2 hours. Yeah. It'll be a 2-hour-long exam. The content will be not quite twice as long as a midterm exam. So our midterm exams are like 3 pages. Final exam will be like 4 or 5 pages, but not 6. 6 is just too many pages.
With 3 questions.
With 3 questions. Yeah, that generally. General rule of thumb. It might look, plus or minus 10% on that in terms of length, but yeah. By the way, that's going to be cumulative, so that's going to cover everything from the start of class to the end of class. So there will be content on there. I'm probably not really going to put any content on the exam from like chapter A, just because that was all supposed to be basically review, but like chapters 1, 2, 3, 4, all fair game, and 5 are all fair game for the final exam. And I'm not going to like specifically weight it heavily towards this content just because we haven't had an exam over it or whatever. It'll be equally weighted over all of the content throughout the semester. Probably that's a relief to some of you to hear that, based on the material towards the end gets harder, right? So yeah, no, I'm not going to make it all hard stuff. It's going to have a pretty even split. So that's our final exam. Any other questions? Okay, doesn't seem like there are, so let's get right into it. So what we've been learning about in Chapter 5 is all of these trigonometric identities. So we've been learning how to disprove trigonometric identities, how to prove trigonometric identities, or verify trigonometric identities, and so on and so forth. So for the most part, for disproving, all we have to do is find an x value for which the identity is not true. Then clearly it's not true for every x value, since it's not true for that one. So that's disproving. Whereas verifying is trickier. There's typically a lot of different ways that we can do a verification. And the trick is to not kind of move both sides past one another. If you do that, then sometimes you can get stuck in like an infinite loop. But what you want to do is basically simplify these guys using known identities, or by rewriting things in terms of sine and cosine, or by trying to find common denominators, add things together, multiply both sides by various things. It's all about simplifying one side into the other. And the biggest tool that you can have here is the tool of not being afraid to try something and maybe it won't work out, okay? That's okay. If you try something and it doesn't work out, you have lost nothing. In fact, you have gained something. You've gained one way in which you know that you shouldn't proceed. So you just have to play with these things for a while until it starts to look better and better and better, and then you reduce to something which is either obviously true, such as this, okay, or you reduce to like a known trigonometric identity, like a Pythagorean identity or a reciprocal identity or something like that, which will tell you that the equivalent statement is true, so therefore all of the other equivalent statements are true. We follow the green line of truth all the way back up to the tippy top where we started the problem, okay? Because all of these things are like saying the same thing in different languages, okay? Or just rephrasing the same statement, okay? So the truth value of the statement is the same as the truth value of all equivalent statements. All right, so that's verifying and disproving identities. And what we learned last time at the very end, I think, was sum and difference formulas. Was this at the very end or what? Yeah, that was just at the very end. So what do the sum and difference formulas say? What they say is, look, cosine or sine of a sum or a difference of two angles, okay, can be rewritten as like products and sums and differences of sine and cosine evaluated at the two angles which we are adding together. So what this does is it allows us to expand significantly the number of angles which we can easily do for like cosine and sine. So let me show you what I mean. If you wanted to do sine of 5 pi over 12, okay, well 5 pi over 12, let's convert 5 pi over 12 to degrees so that we can get an idea of what that would be. So 5 pi over 12 times 180 over pi. We cancel pi, cancel pi. I'm going to cancel 180 with 12. This becomes a 2. This becomes a, what, 60? Okay, we could have gone one more. So 60 we can cancel with 2. We get 30, right? So 5 times 30 is 150 degrees. Okay, so that's like somewhere here. Something's gone wrong. Something's gone horribly wrong. What have I done?
When you divide 180 by 6, it's 30.
Thank you. Yes, Jesus. Okay, so this was 30. And then this should have been 15. So 5 times 15 is 4 times 15, which is 60, plus 15 is 75, I think. Yes? So 75 degrees. So that doesn't look like this. It looks like this, where this angle, okay, where this angle here is 15 degrees, this angle here is 75 degrees. So if we were to make a triangle, okay, and put this inside of the unit circle, there's a problem, which is I don't know how to do this one, because how am I supposed to figure out the coordinates of this point? What I'm supposed to do typically is solve for the side lengths of this triangle, which I can do as long as this triangle is a 45, 45, 90 triangle or a 30, 60, 90 triangle. But this is not. This is a 75, 15, 90. I don't know how to do the side lengths of a 75, 15, 90 triangle. So what do? We just rewrite 5 pi over 12 as the sum of pi over 6 plus pi over 4. Okay, you can write it as the sum of pi over 6 plus pi over 4. If you find a common denominator, right, you'd get 2 pi over 12 plus 3 pi over 12 is 5 pi over 12. So the benefit to this is, even though I don't really immediately understand how to do sine of 5 pi over 12, I know how to do sine and cosine of both pi over 6 and pi over 4. So how does that work? We rewrite sine of 5 pi over 12. You rewrite sine of 5 pi over 12 as sine of pi over 6 plus pi over 4. And then we rewrite that as the product of sine of pi over 6 times cosine of pi over 4 plus cosine of pi over 6 times sine of pi over 4. Okay? And all of those ones I know how to do. Okay, I'm not going to go through them now because I trust that by now you have a pretty good understanding of how to do something like sine of pi over 6. Okay, what do? We do the unit circle, we put pi over 6 on here, we find the coordinates of this point using 30, 60, 90 triangles, right? So since sine gives us the height, for this one, it's a 30-degree angle here, which means that this one's like 1/2, and this is square root 3 over 2, yes? So which is why I replaced sine of pi over 6 by 1/2, okay? I just did that fairly quickly. You don't necessarily have to do it that quickly, but you need to know how to do this without my help at this point. All right, so that's the sum and difference formulas, which was the very last thing that we learned last time. Are there any questions on the sum and difference formulas?
Wait, so for the circle, for like, let's say 5 degrees, how did you convert that to 5 to 6 plus power 4 again? I missed that, I think.
Yeah, so that's the trick, isn't it? The trick is to, look, I don't know how to do sine of this. I know how to do sine of this and this, which, if I add those two together, I get 5 pi over 12. So when you see something like this, what you need to think is, look, I don't know how to do that angle. I don't know how to do that angle. So what tools do I have? Well, if I could express that angle as the sum of two angles, which I know how to do, then I could use the sum and difference formulas to solve this problem. Okay, so it's very much a sort of a backwards thinking type of thing in terms of you think, well, I'm not asking you to figure out how do I add two angles together. What I'm trying to do is ask you, look, I'm giving you the answer of an addition, and I want you to tell me what two things I added together to get this number, right? So it's a bit of like an inverse problem in that sense. So really the form of this, if you want to distill it, would be, look, 5 pi over 12 is equal to x plus y. Subject to the constraint, x and y are one of, like, pi over 6, pi over 3, pi over 4, pi over 2, times any integer n, where n is an integer. Oops. N is an integer. Okay? So this is the type of problem we're trying to solve. We want to find two angles such that if I add them together, I get 5 pi over 12. And these angles need to be friendly for trig functions. The friendly angles for trig functions are pi over 6, pi over 3, pi over 4, pi over 2, times any integer, right? So you can think of the unit circle back in where did I put that? Here it is. You can think of this. Like, what are all of these angles? 4 pi over 3 is just 4 times pi over 3, right? So what I say here is, look, these three angles are friendly. Actually, how about these four angles are friendly, yes? And then if you multiply them times 2, what do you get? You get all of these angles. And if you were to take these angles in the first quadrant and multiply them by 3, then you're going to get these angles down in this quadrant. You see what I mean? So that's what I mean when I give this constraint, which says, okay, look, we want these two angles to sum up to 5 pi over 12. Yes, but that's not enough. We also need them to be angles which I can easily do sine and cosine of. So that's the tricky part, is this type of problem is kind of hard to solve. Okay, what you actually have to kind of think about is, like, well, what sorts of things could x be? Well, if x was pi over 6, is there anything I could add to that? Like, that was like a multiple of one of these other ones that I would get what I want? The answer is yes. If you add pi over 6 and pi over 4, those two will do it, right? But this is a problem where it's not so easy to immediately see that. So if you couldn't immediately see that, what would you try to do? Probably, I would try to make a table of, like, okay, something like this. I would do a table where I would do x, y, and then x plus y. So x could be like pi over 6. What else could y be? Could be pi over 3, or pi over 6 and pi over 4, right? Or I could also make a table of, like, pi over 4, pi over 3, pi over 4, pi over 2, you know, like all of these different combinations, and then I would see, what do I get when I add these together? What do I get when I add them together? And you'll notice, aha, when I do this one, I get 5 pi over 12. So you can kind of do this by a process of elimination, where you can match up all the possible matchups that you can have and see which ones of them could get you 5 pi over 12. But what I did in the problem above was I gave you a hint. I told you that what x was. I told you x is pi over 6. So then you just need to find an angle y such that 5 pi over 12 equals pi over 6 plus y. The easiest way to do that is, of course, to just subtract pi over 6 from both sides, and you will know what y is. So I gave you an extra hint there because I think this is a difficult problem to solve. once you're more familiar with radians, probably you'll be able to see this and say, oh, yeah, 5 pi over 12, that's just pi over 6 plus pi over 4. But it takes time to get that familiar with the subject matter. So this is a really long answer to your question, but do you feel better about it now? Okay. Any other questions? So this was about the sine of 5 pi over 12. Okay, so if on the final exam I gave you one of these, probably you would want to have either these memorized or put them on your formula sheet, which I'm going to allow you to have a one-page formula sheet for the exam.
This big book like this page.
8 by 11, yeah, like letter-sized paper. No poster boards, please. Okay, any other questions on sum and difference formulas before we move on to something else?
It's one side, right? One side. One
Side?
side of the paper.
Yeah, one side of the paper. Should be more than sufficient. There's not that many formulas for this class. There's like interest and then some trigonometric identities. And that's all I can think of. Maybe you want to put like the order of the transformations on there or something like that. That could be a good one. Okay. All right, then let's move on and talk about something else. So we actually already talked about this, but now I'm going to give this a name, which is the cofunction identities. So it's written in a little bit of a funny kind of a way, but they write it in this kind of a way for a very good reason. Okay, so if you have two functions, f and g, and f of x is equal to like g of a minus x, and you also have it the other way around, namely that g of x is equal to f of a minus x, then you call these two functions cofunctions. You could say f and g are cofunctions, okay? The reason that we say that is that basically you can get one from the other by applying the same transformation, right? So what is this transformation? This transformation is like a horizontal shift by a units to the right and a horizontal reflection, right? And a horizontal reflection. So let's see why this is true. Well, you know that the basic shape of sine and cosine are the same. So if you move them over a little bit, you're going to get the other function. So let's see why the first one is true. Let's just take a look at the graph of sine really quickly, and then we'll do a transformation. So sine looks like this, right? So which one do we do first? The horizontal reflection or the horizontal shift? Good. Shift comes first, okay? Horizontal shift is the very first one in the order of the transformations that we would apply. So it says, first of all, pick this whole thing up and move it to the left by pi over 2 units, right? So it would look like this if we moved the whole thing over to the left by pi over 2 units, yeah? This is how it would look if we moved it over. Okay, and then what? We also have to reflect. But take a look at this. When we move this thing over to the left by pi over 2 units, this yellow graph is symmetric about the y-axis. So if I now reflect in this kind of a way, right? If I do a reflection in like this, what am I going to get? I'm just going to get back the same exact graph that I already have drawn here. Okay? So, you know, it's not really a great drawing. It's kind of hard to see that it's symmetric, so I'm going to just copy this one because this one was a good job. And I'm going to put it right there. That one looks better. Now I just need to change it to yellow. Okay. So this is the yellow graph shown here. And we see that, look, so we take this whole thing, we move it over, suddenly it's symmetric, okay? So if you want to go ahead and reflect it, fine. It's still going to be whatever you had before, okay? And we get the graph of cosine, okay? Now you can follow a similar process for cosine, which is to do what? It's basically to take this yellow graph, this is cosine, and what are we going to do? We're going to move it to the left by pi over 2, so that would give us a graph which looks something like this, which looks like a flipped version of the sine graph, okay? So if we were to take it and move it over to the left, it would look like this, yes? Which looks like a flipped version of the sine graph. But if we were then to take this and do a reflection about the x-axis, since sine is an odd function, reflections about the y-axis are the same as reflections about the x-axis. So this is actually going to cause us to have a regular sine graph. Okay? So these are the co-function identities. That's what they call them. We already kind of talked about how you can get one graph by transforming the other. But if you do this specific transformation, then you can do it to sine and you will get cosine. You can do it to cosine and you will get sine. So that's the kind of special transformation which gives you that these functions are actually called co-functions of one another. Okay, any questions on co-function identities? So when would you ever use something like this? I don't know. Maybe if you wanted to do something like this. Times cosine of x plus sine squared of x is equal to 1. If you wanted to prove this identity, you could do so using the cofunction identities. Because what would you be able to say? You'd be able to say, aha, you can't fool me. That's just cosine. So you could rewrite this as cosine of x times cosine of x plus sine squared of x is equal to 1. And then you'd say, and that's just cosine squared of x plus sine squared of x is equal to 1. Boom, verified. Okay, so maybe something like that. Or maybe if you were doing some kind of like tricky integration later, if you take calculus, you could use a cofunction identity to try to clean up your integrand. I don't know. But this is really just saying something about the fact that sine and cosine have the same basic shape, right? That's all it's saying. All right, any questions about cofunction identities? Okay, if not, then we're going to learn one more identity. Actually, it's two more identities. Two more identities and then do a partner practice. And these next two identities are called the double and half angle formulas. And I call them the most important identities, certainly for calculus, but also maybe ever. Well, ever? I don't know about ever, but they're definitely the most important ones for calculus. And there's a very good reason. They are sometimes called power reducing formulas, okay? So typically, you might think that the left-hand side of this is a much friendlier thing than the right-hand side because it's a little bit cleaner to write. But here's a crucial thing. Sine squared is a product of functions. There is a big difference between a product of functions and what we have on the right-hand side. The right-hand side is not a product of functions. It is a transformation of one trigonometric function, okay? Trigonometric functions are bad enough when it comes to calculus without having you to be like multiplying them times one another, okay? When you multiply trig functions times trig functions, the calculus gets very, very hairy very, very quickly. I would much, much rather deal with something which is just, this is just a transformation of a single trig function, right? It's a cosine function which has been horizontally shrunk by a factor of 2. It has been vertically shrunk by a factor of 2. And it has been shifted up like half a unit or something like that. Yes, it has been shifted up half a unit and also reflected about the x-axis or something like that, right? Okay, anyways, the point is there's no power here. We like no power here. Okay, we like no power. So this is why they're super important for calculus. I won't get into why. You'll learn it in your calculus course, but these are the ones that if you were going to memorize some and take them in with you to your next calculus course, these would definitely be the ones that I'd recommend you to memorize. So, double and half angle formulas. The application which we can see immediately is the following. If I want to do something like sine squared of an angle, which I don't know how to do sine of. So you could say, I'm going to rewrite this as sine of x times sine of x. And then if you want to do sine squared of x, all you need to do is compute sine of x once, take that number, square it, and you've got your answer, right? But what if the angle x, you don't know how to do that angle for sine? Well, you could do it as long as you know how to do cosine of twice that angle. Okay, as long as you know how to do cosine of twice that angle. Okay, so this is the utility of the double and half angle formulas for us right now. For calculus, they are literally indispensable. Okay, so just letting you know about that. So what I'm going to do is leave them on the screen. And we're going to try to go into this partner practice here where I want you to try your best with your partner. Maybe I'm going to clean this up a little bit. Try your best with your partner to evaluate these expressions. So I'm leaving them up on the screen here. Go ahead and work with a partner. There's a lot of gaps, so if you don't have someone next to you, please just go put yourself next to someone else, and I'll be walking around to help. Gavin, can you go back and work with Kevin, please? And then Maya, could you come work with Sully today?
Sorry. Sure.
Okay, that's all right. So, you're right? Pi over 12 is 15 degrees. So if we want to do sine of pi over 12, right, what would we need to do ordinarily? Is okay, right? Yeah. Ordinarily, we'd have to make a unit circle, right? and we put pi over 12, which is 15 degrees, that would look like this, right? And we get this like super skinny triangle looking thing, okay? If you expand that, it would look like this. And this length's 1, but this angle here is what? 15 degrees. So this is a 15 degree angle, which means this one's a 75 degree angle. So, exactly, we can't get those coordinates, can we? We could get those coordinates if this is a 30, 60, 90 triangle, right?
Yeah.
But what does this identity do, really, to the input? The angle on the left-hand side is x, which for us is pi over 12 or 15 degrees. What would the input on the right side be? You'd be doing like 30 degrees. Would you know how to do that? See what I mean?
No, because it would be, but it would most of the time it would just be into cosine over 12 cosine over 6.
Okay, so I think you're combining kind of two different things. So you're combining a little bit of this, and also with the sum and difference identities, right? But here's the thing, so for,
I did that, but then you have to find.
wait, okay, so you can start right here. This is fine. What I'd say probably is a little unnecessary is, to break it up here, because this 2 is actually gonna help you here, right? You can simplify 2 times pi over 12, what would I get? Yeah, so it'd be, so you could rewrite this as, forget about this, 1 minus cosine of pi over 6 over 2. See what I mean? So even though I don't know how to do sine of like pi over 12, right?
You just call it.
That's okay, because I can rewrite it as like 1 minus cosine of pi over 6. And pi over 6 is, so we know how to do that, right? Does that make sense? Okay. You get that? Yeah, exactly, so this is sort of unfriendly, this, we don't like angles like pi over 12, it's too small. We can't make a nice triangle and a circle, but an angle like pi over 6, that's 30 degrees, so you can use that to make like a 30, 60, 90 triangle. Yeah. So if I wanted to do this normally, I'd have to figure out what is sine of pi over 12 and then square that number. That's what it means when I write sine squared. But the problem is, I can't do sine of pi over 12. Well, I could. The other way I could do sine of pi over 12 would be to use one of these sines. Oh, that's right. Before that, actually. So anyways, I'd have to use one of the sum and difference formulas. You could write this as like what Mendel was doing, where it's like pi over 6 plus pi over 4, and use a sum and difference formula to get what is sine of pi over 12, and then take that number and square it. But probably a lot simpler is what the square is helping us in the sense that it's going to allow us to use this identity. And this identity allows us to take the angle, which is unfriendly, and turn it into an angle, which is friendly. So from here on, we'll just practice evaluating what that expression is after all. Okay. How's it going in front here? Okay. Any questions? Okay, cool. Okay. Okay. For the first one, so the first one is okay. So this is one valid way of doing this, right? So what did we do? We replace pi over 12 by pi over 4 minus pi over 6. Okay, that's fine. And then you use the sum formula, and then this would give you what is sine of pi over 12, then you square it to get the answer. So that's fine if you want to do it that way.
So 2 times.
No, that's okay, this is totally valid reasoning, but it's maybe a little bit more work than we need to do, because we have these double and a half angle formulas, which say what?
One minus.
Sine squared of pi over 12, if I were to use this formula, how would I rewrite it? I could rewrite it as 1 minus
So it's
cosine
2 times
of
12.
something divided by 2.
Or it'd be 2 pi.
Where the angle inside on the left hand side is just x. But the angle which should be inside on the right hand side should be 2x. So if x here is pi over 12, what angle is going to go in here?
Shouldn't these be?
2 times pi over 12, which what is 2 times pi over 12? If I simplify it, what would I get?
We have a 2 here,
Pi
and
over
we
6,
got
right?
this. And this
So why is
is
that good? Because now I've got an expression which is cosine of pi over 6. That's an angle that I know how to do.
Did you get, you did 1 minus square root 2 over 2?
Yes, this one's gonna be, yeah, so it's gonna be 30 degrees, right? So 30 goes inside of the unit circle, so 30 is gonna go up to this point, this would be 1/2, this line could be square root 3 over 2, like that. So yes, cosine of pi over 6 is square root 3 over 2. So you can just replace this by 1 minus square root 3 over 2 over 2. Make sense? Right, so if you have to negative 3/5, right? See what I mean? So it's like we take these cosine squared or sine squared where the angle inside is like half of the good angle. You know what I mean? And then we multiply it by 2 and suddenly we have an angle which we know how to do, right? Are y'all finished? Yeah. Alright, so we get for your angle in the first one, simplify it after 5 or 6. Okay, and then the second one, what do we get?
It's easier.
Yeah, so negative.
Oh, I mean, I don't really think you.
Yeah.
Like, it's just like, you can't get.
Pretty sure partly on this. I mean, you can simplify if you want. Like, you can write that as 1/2 minus square root 3 over 4. I mean, technically it's improper to have fraction of fractions. But if the problem didn't say simplify completely. The problem didn't say simplify completely. Yes, exactly. Math is all about semantics. It's entirely semantics. Sine of pi over 12, you rewrite as 1 minus cosine of pi over 6. Do you see the utility? in
Yeah,
that?
don't use
In the
tab
sense
box.
that this is not a friendly angle. Pi over 6, you're doing that for what's in the one difference here is when you use pi over 6, it's 30 degree angle.
Well, those signature things, I don't like them. Yeah.
So,
No, I read it with just water to
okay,
rinse
but
it.
here we've
If
got
I'm
this,
right
right?
now, but it's really not.
Cosine of pi over 6 is actually
Well, most of that hair is
So,
mine, so.
This one, what do we get? Cosine squared. The only difference is this, I guess you have a plus and minus, right? The way I like to remember that is sine is minus. That's just how I remember it. Okay, but anyways.
She's cute.
Cosine squared,
This,
we get
she's
1
just
plus,
fresh.
and then negative 3 pi over 4. Suddenly, negative 3 pi over 8, that's like, I don't even know what that is, that's like,
You have to be very
that's like 37.5 degrees, negative 37.5 degrees, I don't know what that is.
Okay, but
I like negative 3 pi over 4, that's.
Which already have
right?
stuff to furnish
So-
the entire house because my parents are moving
So how
and
are
they're
we
getting
gonna
rid of a
divide
bunch of
it
stuff.
before?
you're not from here.
Around this way.
I live 30 minutes down the road. And I can just bring this to
I'm in the wrong one.
Take us so I can just bring there's couch if I wanted to.
To get a couch here.
So let's start
Yeah, which would imply that you would have
at
to
0,
buy
and
some
then we're
couch.
gonna go,
Yes, exactly.
it's
Like,
negative,
to
which
ship a couch from home here, it would really cost as much as
for
a couch.
clockwise, right?
Just order them.
So,
That's not how it works.
I
Anyway, I
would
had to get.
be like,
I had to-
Overnight
that's
is
what
what
I'm saying, is
Amazon-
like that would take.
and then what would
Like, that
be
would, I
straight
would have to
down,
pay
that would be.
overnight, and it would be just as expensive for a couch. Are you just gonna do
Ooh.
Hell to the no. I like this.
You
one.
drive down here?
No, I flew.
Negative
shipped all my
3.4.
How much was
A lot.
But
I'm
one
sure it was
negative
a lot of money.
so-
But you know what? I don't drive, and my parents were like,
How far is your away?
How far away is it?
All right, are we done? Okay. Have a good day, y'all.
Like 15 hours?
Like 10 hours.
No, that's not that long.
I will